Greetings everyone, I am Jaber Ibn Abdul Hakim from Team Synthesizer. We are supervised by Dr. Sheikh Anwarul Fattah from Bangladesh University of Engineering and Technology. We are happy to present our work about synthetic speech attribution in IEEE Signal Processing Cup 2022. Before we dive deep into our methodologies, let us look into a scenario. Perfectly imitating or recreating one's voice could possibly lead to identity theft, media manipulation, and widespread fake names. As introduction of new technologies are opening endless horizon of possibilities, it is also important to keep in mind about possible drawbacks. As synthetic speech generation is a common technology nowadays, it is a necessity to have a system that could differentiate among the audios originated from different sources. Keeping that in mind, this year we are tasked to identify the algorithm that was used to generate the audio. The problem also included the correct identification of audio samples that were generated from an unknown source. For this competition, we are provided with a total 7,000 samples. Algorithm 0 to 4 had 1,000 samples each. We have marked class 5 as a class of unknown algorithms. There were total 2,000 samples for this class. First 1,000 were provided at the start of the competition, and the rest 1,000 were provided with the final test set. For evaluating performances of the methods, there were three parts altogether. In first part, there were 9,000 samples available for testing. For each one of them were clean audios. Following, for part 2, there were another 9,000 samples, which were all augmented using different methods. And for last and final one, for part 3, we had 10,000 samples of audios that contained presence of both clean and augmented samples. While trying to solve the problem, we face some specific challenging cases. First of which is small training dataset. As specified earlier, there were total only 7,000 training samples, but test 1, 2, 3 together had 28,000 samples. So it is very much possible that the training sample does not cover the entire test dataset distribution. Following to that, we had only 5 specific algorithms to work with. It can easily be assumed that number of possible algorithms is pretty huge. So it's totally impossible to learn about all unknown algorithms. Perturbed samples were present in test 2 and 3. In test 2, the audio samples were perturbed with random noise, reverberation, and different compression rate. And in test 3, both normal and perturbed samples were present. Another problem that we had to deal with was speaker overlap. Algorithm 0 contained single speaker, algorithm 1, 2, 3, and 5 contained same speaker, and finally there were multiple speakers for algorithm 4. This information was extracted completely based on our thorough observation, and it might not completely be true, but we observed large number of samples to draw this conjecture. To come up with a viable solution that generalizes on both training and testing data, different modeling approaches were taken. Some of them are listed here. We used XGBoost with random forest, LSTM and transformers, autoencoder, arcface and KNN filter, low probability filter, and finally, multi-class classification CNN model. Of them, the last one performed better. After many experiments, the overview of our final methodology jotted down to this. Along with provided dataset, we used some external dataset. After resampling all the audios to 16 kHz, log null spectrograms were generated and few augmentations were applied on them. After that, the spectrograms were passed through different CNN models. For prediction, the output of different models were assembled together. The generated test labels were used as pseudo labels to train the models again, along with original and external dataset. And finally, after assembling their predictions of test dataset, the final output was generated.
Hello everyone, my name is Muhammad Afsaf Rahman and I'm a third year EEE undergraduate student at WIT. In this section, I'll discuss the external dataset part of our solution. Our external data can be divided into two categories, namely synthetic data and natural data. For synthetic data, at first, we converted audio data to text data using Wave2Vec 2.0 automated speech recognition model. As there were some spelling errors in the text, we corrected them using natural speech corrector model. Finally, we converted the corrected text data back to audio data using different text-to-speech models. Here's a list of text-to-speech models that were used for text-to-speech conversion. As newly generated synthetic data couldn't address issues like speaker bias, lack of diversity in the unknown algorithm, we added the natural speech data as the unknown algorithm. For natural data, we added three publicly available datasets, namely AlgoSpeech, LibreSpeech, and VCTK dataset. AlgoSpeech dataset contains nearly 13K short audio clips of a single speaker reading passages from 7 non-fiction books, whereas LibreSpeech dataset consists of approximately 500 hours of English speech from over 1,200 speakers. Finally, VCTK dataset comprises speech data from 110 English speakers, where each speaker reads out about 400 sentences. Let's look at our final data distribution after including the external dataset. As you can see from the figure, it contains approximately 7K computation data, 6K LD speech data, 6K VCTK data, 6K LibreSpeech data, and finally 18K synthetic data. Let's move to the data pre-processing part. Before feeding data to our models, all data has been pre-processed using the following step. At first, audio data is resampled to have 16K sample rate. Then audio data is normalized using Z normalization. Finally, audio data is converted to Mount spectrogram using short time Fourier transform.
Hello everyone, I am Bishwapal, a third year on IEEE undergrad, and I'll be presenting the augmentation part of our proposed solution. We performed augmentations on both audio data and spectrogram data to make our solution more robust and to increase the capability of the models to generalize. As mentioned by my teammates, some of the test datasets had noise, reverberation, and compression in the audio samples to resemble real-world cases more, whereas our original training data is without these issues. To make our models more robust to these issues, we introduced similar augmentations. Here we display some of them. This is a small portion of a data sample in the trained dataset. Upon applying reverberation augmentation here, we can observe that there are slight changes in the audio sample. We also randomly added Gaussian noise to the training sample, which made our data more noisy. Furthermore, we applied compression to the audio data. Here we can see that the compression added subtle changes to the time domain signal. Next, on the spectrogram data, we added some more augmentations. Here we try to address the issue of training our models on a dataset where there are multiple speakers. Since it is a real possibility that the models might overfit on the speakers instead of the classes or algorithms, training the models to distinguish between them is quite crucial. To that end, we apply two augmentations, mix-up and cut-mix. We are demonstrating the mix-up augmentation first. Here we take two spectrograms and then we take one of them here and overlay the other spectrum on top of it. Cut-mix augmentation is a little different. Here, instead of overlaying, we cut out pieces of one image and place it on top of another. In the spectrogram, we also randomly masked a few stripes in the frequency and time axis. This mimics the famous cutout augmentation widely used in computer vision problems. So these are the augmentations that are used to reduce overfitting and increase model robustness to the different challenges presented by the test cases. Now let's move on to the models part. To leverage the boost provided by the transfer learning, we initialize the models using ImageNet weights. In part 1, our top models included Efficient and B0, ECNFNetL2, ColumnX, ResNet models, etc., which showed a good amount of CVLV correlation. Finally, their predictions were ensembled to get an additional boost in score. In part 1, we used smaller models to take advantage of their lower computational cost and still got strong performance. Similar to part 1, we leveraged transfer learning in part 2 as well. Here, our top performing models also included Efficient B2S and ResNet 50. As you can see from the graph, their ensemble had a very good CV and LD score. Now, let's move on to the ensemble part.
Hi, I'm Najibul Haq Sharkar, a third-year CSE undergrad, and I will be presenting the final part of the slides. So after we train the various models mentioned before, we ensemble their output. We take the outputs from model 1, 2, 3, and so on, and actually take their mean as the final prediction. So this combination of model outputs actually increased our overall score. So moreover, we actually introduced a semi-supervised learning component to our method. We had a lot of unlabeled test data and we wanted to find a way to utilize it. So first, we trained teacher models on our labeled datasets and got its predictions of the test set. So you considered these predictions as pseudo labels and included them into the training set for the subsequent student models. By training in this way, we can also mitigate the effect when a test dataset has a very different distribution than a trained dataset. So this method consistently raised our score, and we actually combined all these techniques we just described to construct our final method. So as mentioned before, we tried a lot of techniques before arriving at our final one. So first of all, we tried some tree-based methods. We extracted the embeddings from ImageNet models and then passed them through XGBoost and Random Forest. So LSTMs and transformers have been successfully used in the past for audio classification, so we also experimented with those. We also used autoencoders, where the model output is actually the reconstruction of the input. Furthermore, we saw that if we train a CNN model using the 5 known classes, they tended to have high confidence for validation data of the known class and low confidence for the unknown class. We utilized this property by using a low confidence filter and classified confidence under a certain threshold as the unknown class. So ultimately, our best method was the multi-class CNN classifier trained using the provided 6 classes, which boosted our score above 0.9. We paired this with a method called ArcPhase, which encourages embeddings of similar classes to cluster together. Then we used the k-nearest neighbor algorithm to filter out the unknown classes, which increased our score. But ultimately, when we applied additional methods such as external data, augmentation, and pseudo-labeling, the boost from the filter dropped as the original CNN models became more accurate in their predictions. So, in the end, we chose the multi-class CNN method as our final method. Now, let's take a look at the results of our model in test 1. So here we compare our baseline method of the CNN with cumulative additions of external data, data augmentation, ensemble, and pseudo, which shows how the score tended to grow as more methods were added. So similarly in test 2, all the methods cumulatively increased the overall score step by step. So these high results and the CV-LB correlation gave us confidence that our models worked really well and were robust. So let us take a look at the prediction distribution of our method for all the 3 parts of the competition. For part 1, our method predicted about 1500 samples for each of the classes, the same for part 2, and for part 3 we saw that the model predicted a high amount of unknown class. So before concluding, let us revisit the challenges we presented before and see the solutions we offer for each one. So initially, the training dataset was small compared to the overall test data, so we used external datasets to increase training samples to solve this problem. Furthermore, to compensate for the low amount of unknown test cases compared to the known ones, we created external unknown class data via various methods. Also, we applied semi-supervised training so that the effect of the different distribution of the unknown test class is mitigated. In order to tackle the perturbed samples introduced in part 2 of the competition, we applied audio augmentations using random parameters, which ultimately made the model more robust. To overcome the multiple speaker problems, we acquired external data which contained different speakers. We also applied mix-up and cut mix in order to make the model speaker invariant. And finally, to tackle the data distribution imbalance created after introducing external datasets, we used macro F1 score instead of accuracy as our evaluation metric. So from the results shown previously, it is quite apparent that we have successfully circumvented these challenges through our methods and ultimately made a robust solution for this competition. So that actually concludes our presentation. We appreciate you for listening patiently. Now please feel free to ask any questions you may have.